So today's lecture is actually, we're going to skip around a little bit here. We were originally going to have, today was originally a overflow day for sort of making up missed lectures. And I decided instead, actually, because our homework's out on Wednesday and it's going to cover machine learning, I actually wanted to start the machine learning lecture today. And it's actually okay if we're going to miss one lecture, it's good. It's that last one. We actually didn't do it last time either. It's good to know about spatial information and GIS systems, but they're a much more specialized topic, and it's sort of much more niche than a lot of the other topics we covered so far. So I think it's okay to actually miss it. What we're actually going to do, which I did last time too, is last offering of the course, is that for the tutorial, so the tutorial assignment is going to be out this Wednesday. And for that, I will put up a demonstration tutorial, kind of like an example of what kind of things we're looking for. And that will actually cover GIS systems to a certain degree. So you can learn a little bit about it by following the tutorial. And you can follow along and kind of, learn some of the Python libraries you can use, like GeoPandas, these kind of things. And then it'll have some pointers to learn more for those that sort of want it. But I think it's more important to start this section because your next homework is going to involve a lot of machine learning. Okay, so this is actually a pretty big switch now in the course. So prior to this, we've largely been focusing on kind of the management of data, right? We kind of drifted a little bit towards analysis and certainly some machine learning in the last lecture on free text. But for the most part, it was really about kind of how we dealt with basic data sources and basic sort of ways of storing data, right? So relational data, matrices and vectors, free text data, graph data, right? And now we're going to switch, and now we're going to spend the next large portion of the course talking about machine learning and general sort of statistical methods for analyzing data. Now, I think this course is actually, as a whole, though we haven't seen it yet, it's actually quite machine learning heavy. This is both my own biases I'm sure I'm bringing in. I do work in machine learning, so I'm naturally going to sort of emphasize those points a little bit more, I think. But I also think that when you look at data science positions, kind of the positions that are out there and the positions that I've interacted with, they do tend to be pretty heavy on machine learning and statistics. So while there certainly is the need to understand how to write code and understand how to write parsing algorithms, stuff like this, they're also very heavy when it comes to actual sort of knowledge of machine learning and statistics. So we're going to spend a pretty large amount of time on that, both on kind of basic machine learning and really basic statistics. I mean, nothing we're going to do for the first several lectures is really modern machine learning in any way. But then we're also going to cover some other methods, more specialized methods like recommender systems or basic deep learning systems and stuff like that. So we're kind of go quite deep into some topics, but also hopefully in a way that emphasizes kind of how these are used in practice and how you might actually use them to solve some data science problem that you're presented with. Okay, are there any questions so far before we jump into this next sort of major section of the course? Okay, so let's get started. So today we're going to start by talking about a simple example, and kind of actually the simplest example, I think, of machine learning, which predates machine learning by a good 2 centuries, at least the name machine learning by a good 2 centuries. I mean, Gauss was doing linear regression a long time ago. And we're going to start really with a simple example about fitting a line to data, which is actually, though it seems very simple, is actually kind of the concept you want to think about when you're thinking about machine learning, at least when you think about supervised learning. Then we're going to jump in and talk about machine learning in a little bit more general terms. We're going to describe some machine learning notation, and I'm going to try to emphasize a kind of framework that all machine learning algorithms, at least for now, all supervised learning algorithms really fit into. And this really spans, simple linear regression all the way to pretty advanced deep learning. We're then going to sort of revisit linear regression under this new framework. So we're going to figure out how we can use this framework to sort of understand the mechanics of linear regression. And finally, I'll talk a little bit, if we have time, about matrix and vector notation in analytic solutions. We actually have the next sort of 3 lectures really for a combination of this, a little bit more advanced look into linear regression, and then finally linear classification. So we do have plenty of time to study these topics, so I'd rather go slowly over the first part than rush to get the end here. So stop me if you have questions. This part is definitely from a math perspective, so from a coding perspective, it's probably easier than some of the things you've known so far. So nothing is sort of as computationally hard as like writing a parser, sort of algorithmically difficult as writing a parser. The algorithms of machine learning are actually all quite easy, but the math does take a little bit of time to get used to. So the various notation I use will be a little bit daunting if you haven't seen it before, but it all is actually quite simple. So hopefully you'll sort of get familiar with it pretty quickly. Okay, so let's jump into least squares regression. And I want to start this with a question. This is actually how I sort of teach machine learning in a lot of different courses. But I want to start with obviously different levels of detail. But I want to start with a simple example here, which is the example of predicting electricity consumption in Pittsburgh. So my question for everyone here is, what is the electricity consumption of Pittsburgh going to be tomorrow? All right. Any guesses? What it's going to be? Right. You probably have no context for even knowing what those amounts are, right? Because and the reality is actually this is not a sort of a random occurrence. It's actually very difficult to build kind of an a priori model about something like this, right? So that is actually, even if you knew the units involved in power and all that kind of stuff, it's actually kind of hard to know, how do I model the power consumption of an entire area like Pittsburgh? And actually, knowing what the biggest consumption is tomorrow is actually a very important problem, because it lets us know how to schedule generators. And some generators, like coal generators, need to have a lot of time to start up. I mean, the way coal generators work is they boil water. That takes a little while before they start generating electricity. So you have to start kind of well in advance. And we really need to know well ahead of time how much power we're going to need tomorrow. So this is actually not a hypothetical problem. This is a problem that the operators for Pittsburgh solve every single day, and actually every single hour, and maybe even more frequent, and sometimes even more frequently than that. And the problem is it's really hard to sort of know this ahead of time, right? So I could, come up with a model about the kind of devices I use. I could say, okay, I'm using my laptop right now. My laptop uses 60 watts of power. I use this and this and this, and I'll come up with all these things and kind of build a model of myself and my actions, and then extrapolate to everyone else. But that's actually incredibly hard to do. So most models like that people kind of come up with end up being pretty actually far from reality, and they have to be tweaked a lot in order to get anything that looks even close to sort of real scenarios. So this is actually pretty hard to do. It's hard to build models like this kind of from first principles. But what's relatively easy to do is to take look at past historical data, look at relevant features that might impact electricity consumption, and then just record what the actual peak demand was. Okay? So let's just do that. The one sort of relevant feature we're going to focus on here, though we'll focus on others later, is high temperature. So at least in the summer months of June through August, consumption in Pittsburgh is largely driven by air conditioning. That's their biggest that's sort of our biggest consumer of electricity, at least. And so you would expect that, with higher power might come higher consumption of electricity. So let's just take a look at that. Let's plot all the days. We're going to actually plot all the summer days only. We'll eventually get back to winter days in a later lecture. But let's just plot all the summer days, either June through August, for the last 5 years, and look at the temperature and what the peak electricity consumption was. So this is the peak demand in gigawatts. This is the high temperature in degrees Fahrenheit. And as you can see, it sort of follows a pretty nice pattern here, right? There's, as you do expect, as the high temperature goes up, so does the consumption. And now suppose we kind of want a model to predict what's the temperature, what's the consumption going to be tomorrow. So for example, if the high temperature with tomorrow was going to be 75 degrees, as I actually believe it is going to be 75 degrees tomorrow. Normally this is reserved for summer months, but it's supposed to be 75 degrees tomorrow, I think. It's the one time I taught this course in the winter where this is actually a relevant question to ask right now. The question is, what do we think the demand will be? So we sort of think here that there's something like a line that kind of models this data, right? So let's hypothesize that we can model our peak demand, or at least come up with a good prediction, with some linear functions. Modeling the peak demand is some linear function of high temperature. So in other words, some coefficient on high temperature plus some bias term. Right? This is the slope and the intercept of our line that we're going to fit to this data. Right? So again, we're going to hypothesize that peak demand is is a theta 1. Theta 1 is just a parameter we're going to try to find times the high temperature plus theta 2. And that's going to be our model for how we predict what the high temperature, what the peak demand is going to be tomorrow. So now the sort of key question here is, how do we find a good fit to the data? And it seems like sort of an easy question, at least in this context, and it actually is pretty easy in this context. Not only can we do it the way I'm going to show you, we also can actually just find an equation that gives us the exact solution in this case, which we'll do kind of actually later toward the end of this course or next time. But I actually want to do this in kind of a very generic way. So I'm going to use this as an example about how we might find kind of good fits to data as a whole. And the intuition here is that we want to come up with some measure about how good our approximation is on the past data that we've seen before. Right? So I'm going to sum over all their days. This means the days in our data set, by the way. This means days sort of in our table of past days. So we're looking towards the past. And we're going to say, how good is this fit over the past? In other words, if I take the high temperature on that day, remember I sums over all the days, multiply by theta 1, add theta 2, and subtract the peak demand, then take this quantity and square it. If that quantity is big, it means we're not doing a great job of fitting the data. If it's small, it means we're doing a reasonable job of fitting the data. Okay? So now our goal, and I'm calling this function E, really sort of for error. It's also sometimes called loss, but I'll use error here, kind of to say the function that we would like to make small. And this is actually going to be kind of the framework by which we think about machine learning in general. So we'll get back to more of that in a second. Okay, so I'm going to actually have a little bit of notation here. So I'm going to call the high temperature for some day, just for simplicity. It gets kind of tedious to write high temperature and peak demand every time. So I'm going to call the high temperature xi, and I'm going to call the peak demand yi. So again, here we're just going to, this is just for this section of it. We're going to say that xi is just going to be a real valued number, right? That's the high temperature for that day. And yi is another real number, which is just the peak demand. So our error function in some way, which I'm writing as a function of theta, because again, theta are our parameters that we're going to eventually tune to make this function low. Our error function is a function of theta. I'll even write it as a function of theta 1 and theta 2. So those are our two parameters. This equals a sum over all I in our days, in our data set, of theta 1 times xi plus theta 2. This is our slope times the high temperature plus our intercept minus yi. And we're going to square it. Now, why do I do squaring? I won't worry about that right now. We could take the absolute value too. That would be perfectly reasonable as well. It turns out people use the square, I think, just because it ends up with an easier solution in the end. But we'll get to that in a little bit. Okay, now here's the key idea. So suppose we want to sort of minimize this function. We want to find the values of theta that make this function small. The key idea we're going to use here is the idea of the function's derivatives. Okay, so we are going to use calculus here, but it's really simple calculus. It's just derivatives. That's actually the only kind of calculus you really use. In all of machine learning really is just, not all of it, there's some other stuff in probability maybe, but a whole lot of machine learning is basically just derivative calculus and nothing fancier than the chain rule. So that's really what we're going to use here, and that's it. And in fact, even all of deep learning is just the chain rule and derivative calculus. So there is calculus, but it's really simple. There's no integrals or anything we're going to do here. It's just really simple stuff. But, okay, let's say we have some function. So I'm going to call this function f of theta. And this dimension here is theta. And I want to find some sort of minimal point of this. And actually, assume for now this function kind of curves upwards. There's no reason for that actually to be the case a priori, but the functions we'll care about, like that error function there, do actually happen to be ones that kind of curve upward. So there's actually going to be only one kind of minimal point for functions like that, and there's kind of, you know, it's the lowest point possible in the function. So okay, so remember that the derivative of this function at a point here, so say this point here is theta 0 or something like this. So this point here is theta 0, and the derivative at this point is just the slope of the function at that point, right? It's just the slope. It's the rate of change of that function right there. But importantly, and sort of you learn that, you know, you can do a lot of things with a derivative. But what's important for us is that the derivative tells us which way of the function is down and which way is up. Okay? Because over on this side of the function here, right? So this is sort of the minimum. Over on this side of the function, the derivative is always negative, right? The derivative always has a negative slope. And over this side of the function, the derivative is always positive, has a positive slope. So when the derivative is positive, we want to move the other way, in the negative direction. And when the derivative is negative over here, we would like, so when the derivative is positive, we would like to sort of move this way. We want to move towards the lowest point. And when the derivative is negative, we want to move this way. In other words, we want to move in the direction of the negative derivative of this function. And that's really the key, actually, of almost, that actually is the workhorse of all machine learning, is just move in the direction of the negative gradient. It's how all these things work on some level or another. With some fanciness, but that's pretty much it. So I should say, right here, I'm using, in this slide, I'm using the notation. This is just a little bit of a notation here. So I'm using the notation here, f prime of theta for the first derivative of the function f at theta. But it turns out that when we have functions that take higher dimensional inputs than just a single variable, this notation doesn't really cut it. So we're just going to use another, you know, it's a little bit more cumbersome, but it's very common here. We're going to use a notation called partial derivatives. So the idea here is if I have a function, so suppose I have a function f, which takes as input vectors in Rn, so say theta is a vector in Rn here, and outputs real numbers, then I'm going to define the partial derivative of f of theta with respect to theta I. Sorry, I'm actually going to use theta j. So to theta j. I'm going to sort of use this for my notation about what the derivative is of that function with respect to that one parameter, that one input, theta j. Okay? Now the reason why I use this sort of partial sign here is just, this is just sort of the convention. When this function depends on more than just theta j, you don't call it a total derivative, you call it a partial derivative. There's a more formal definition than that I don't want to actually get into here with sort of the differences involved about, you know, whether you're taking a derivative of the entire thing or just sort of a single part of the function. But just from my perspective, all that I am doing when I use those partial derivative signs is I'm just saying the function depends on more than just theta, but I'm just going to be, or theta j, but I'm going to be just differentiating with respect to theta j. Okay? So really getting familiar with the notation is actually the hardest part. We'll see an example of this in a second, so it'll hopefully be clear. But again, it's actually kind of cumbersome even in the example we'll see. So just be aware of that. Okay? All right, any questions so far? Yeah. That's a good question. Why do we want to minimize the function? Right, so the idea here is that we want to find some good fit to the data, right? We want to find some parameters, theta 1 and theta 2, that kind of seem like they actually fit the data. And the function is essentially our measure of how well we are fitting the data. I mean, if this function is big, this means that our prediction here is very far away from yi, right? But if it's very close, it can't be perfect because we know a line can't pass through all those points simultaneously. But if it's small, this means that we have a line that seems to actually kind of fit the data itself. Okay? So that's why we want to minimize that function. Yeah. Yeah, could you take the, could you take the yi and say yi minus theta 1 times xi minus theta 2? Yeah, that's fine too. It wouldn't change anything actually, because those functions are equivalent, right? If you square a function, it doesn't matter if it's a minus b squared equals b minus a squared. So it actually wouldn't matter which way you do it. Yeah, it has no effect on it. Okay. So let's sort of dive in now and compute the partial derivative of that function with respect to theta 1 and theta 2. And that's going to be our, and then we're going to take, what we're going to do is we're going to take small steps in the directions of those partial derivatives. And that's going to be how we make our function, our approximate our hypothesis, fit this data. Okay? I'm going to actually show you what this looks like in a second. But first, let's derive what these things are. Okay, so here's the nasty slide of the math. But I'll take it sort of step by step here. It's actually not that hard. It's, again, just derivatives and the chain rule. Okay, that's everything you need to know about calculus to do this whole course. Okay, so I'm going to write the partial derivative of my energy function, or sorry, I'm calling it energy function, error function, with respect to theta 1. Let's do theta 1 first. Okay. So this thing equals partial derivative with the theta 1 of the sum over all I in my days of theta 1 times xi plus theta 2 minus yi squared. Okay. The first thing I'm going to do is I'm going to bring in, when you have a derivative of a sum, that is the same as the sum of the derivatives, right? So the derivative can be moved inside and outside of sums. That's sort of a basic rule from calculus. So this is going to be equal to the sum over all I in the days of the partial derivative of theta 1 times this thing. Okay, so now is where I apply the chain rule. Okay, I want to take a derivative of, of this thing. Oops, this is a square here. I want to take a derivative of this thing. So the way I do that is I take the derivative, basically, of this whole expression here, times and differentiate this sort of whole outer expression, times the derivative of the inner expression, right? So this equals, again, we have our sum on the outside. If you have a function like x squared, the derivative of x squared is just 2x. So it's 2. Oh, actually, I forgot a 2 in my notes here. Oh well. Doesn't affect things actually. It ends up being a scaling factor. 2 times this thing without the square here. X theta 1 x1 plus theta 2 minus y I without the square, right? Because I'm get rid of the square when I'm differentiating it, times the derivative of the inner thing. Okay? Now the inner thing, of the inner terms, only this one depends on theta 1, right? So the derivative of this is going to be 0 with the theta 1, the derivative of that with the theta 1 will be 0. So this will be times the derivative with respect to theta 1, partial derivative of theta 1, of just this first term, theta 1 x I. Okay? And this is just, the standard thing. The derivative of c times x with respect to x is just c. So this is equal to the sum over all days, 2 times theta 1 xi plus theta 2 minus yi times xi. Okay. So that's really the entirety of our math here, of our calculus here. Does anyone have any questions about that? Because while that is actually as hard as it will get in some ways, kind of amazingly. I want to make sure everyone kind of follows that, what I did there, because if it's been a while since you took calculus, that might not be completely obvious. The general rule that I'm applying, which is the chain rule here for just one-dimensional functions even, is that if you have g of, well, actually, if you have h of x equal to f of g of x, then the first derivative, the derivative of h of x equals the derivative of f of x just applied to g times the derivative of g. So that's essentially the rule I'm applying here, which is the chain rule. I'm applying that in this line here, where I take this term, take its derivative, put it here, or take the inner term here, put it here, then take the derivative of the inner function there. Yeah? What happened to the integer 2, did you say? Yeah, I just forgot the 2 here. It doesn't actually matter because it ends up being just a scaling term where it's going to take a small step by some constant. And I often forget to add the... It's actually more common to put a 1/2 in front of these things just so you can avoid it, just so the 2's cancel out. But I just forgot. I'll edit those slides and put it there. But there should be a 2 there. Yeah, there should be a 2 right here. And in a similar way, again, modulo the missing 2. If you do the exact same thing with theta 2, the exact same logic will hold, except on the outside here, you only have a theta 2 term. And so that would just be 1, right? So you would have just this term here. So you also have that, the derivative, partial derivative, or error function with respect to theta 2 is just equal to the sum over all our days, 2 times theta 1 xi plus theta 2 minus yi. Okay. So those are our derivatives. So now, let's see what the algorithm is to actually optimize our function. And again, I'm kind of going through this in a little bit of detail here before I show you what actually happens to the function, because I do want to emphasize that this is really all it is. This is all that you're doing to sort of solve this model fitting problem. It's just these updates. Okay, so how do we find the best value of theta? Again, this is the theta that minimizes the error. In other words, the one that sort of gets as good a line as you can to that data, at least as good as you can as measured by this squared error term. So all we just do is we just repeatedly take steps in the direction of the negative gradient for each parameter. Right? So we have 2 parameters, theta 1 and theta 2. And each time we just repeat, we just take their value minus the partial derivative with respect to each of those. And we just repeat that updated again and again. And this is the gradient, it's called the gradient descent algorithm. We'll define what sort of the gradient is a little bit more formally in a second. It's just really a vector of a lot of partial derivatives, but won't worry about that for now. But this algorithm, and I should say, this alpha here is just some small positive number called the step size. It does actually impact a lot, sort of your choice there, but this is a parameter you have to pick. To see how far you want to take a step. We will talk a little bit more later about how you go about picking that kind of stuff, but we won't worry about it right now. And this procedure here is called gradient descent. And it is really no kind of lie to say that this is the workhorse of all modern machine learning. So every single machine learning system you encounter, very few exceptions, but pretty much all of them that you encounter, the ones that recognize faces, the ones that recognize images, everything, they're all just based upon, a version of this. Okay, so let's see how this looks. All right, so here is our data set, our high temperature and peak demand. And one issue here, which I do actually have to, because I'm going to give you the code for this, so it's easy for me to fudge and sort of say that this works on this as I wrote it. But if you actually run it, it won't work on this. Actually, we'll just sort of, well, we'll guess in a second what it does. The problem here is that the two dimensions you have in this function are very differently scaled. So remember, you have an offset, basically, how much, what's your intercept term, and you have a slope term. But the units here on your slope are actually quite large, right? These units are degrees Fahrenheit, and they're pretty big relative to the units you have on your basically your intercept term, which is essentially units of peak demand. Okay? So if you actually run gradient descent just like this on these raw features, so where x is the high temperature, it actually won't work. And you can try. If you tune it just right and run it for an incredibly long time, you can get it to work. But it probably won't work. This is actually a common problem. People see this algorithm, they implement it, and then it doesn't work. And it's usually because the things aren't scaled properly, at least the first time you try to implement it and run it. So I actually am going to be completely honest here. You have to do another step before you can do this. You have to normalize the input. All right, and when I say normalize, we'll go over this a little bit more later. But all I mean here is that I'm going to take the xi's, and I'm going to subtract. Oops. Sorry. Thank you. I'm going to take. So I'm going to normalize these things. I'm going to subtract their mean off. I'm going to divide by the standard deviation. These are not, by the way, these are not normally distributed or none of that. I'm not trying to make it like a Gaussian random variable or anything like that, for those that sort of know that terminology. I'm just making it more in the range of the other units. So that's sort of why we're doing that. And you might also, if you were, this one's actually already okay. You might want to normalize that one too. It's less common to normalize. Often you actually don't need to normalize outputs nearly as much as you have to normalize inputs. But it won't work if you do this. You have to actually take this next step. So I'm going to do this to all my. I actually, in this case, I don't have to change the y, so I'm not going to. But I will change all the x's. Yeah, question. We're going to ask that in a second. Actually, I'll cover that in a second. Question was, why doesn't it work? We'll see what happens. Yeah, question. And the question is, how do you choose what to normalize? In general, all the inputs, every single input, and they're going to be, we'll see in a second, there's more inputs possible than just one input dimension. They should all be normalized. So it's not a hard and fast rule. And there are cases where, for the cases of like maintaining sparsity, you actually don't want to normalize them. But even there, again, if you do like your PageRank trick, which you're all very familiar with at this point, to subtract something without actually subtracting it, you can do the same trick here. And so, in general, all your features for most machine learning algorithms should be normalized before you apply it. If not, again, this is sort of a practical thing. It's just a matter of sort of practice. A lot of libraries will pre-do that for you. Will just do it for you ahead of time. But just as a general comment, especially if you're running gradient descent. It's important these have somewhat nearby relative scales, and so you have to do this. Okay, so I'm going to do this, and again, this is just sort of in full. I want to describe everything I'm doing here. So I'm going to actually show you that I'm actually no longer have temperature on the x-axis anymore. Now it's this weird normalized temperature in some units that don't actually exist. That come up after subtracting the mean and dividing by the standard deviation. But importantly, actually, there's nothing wrong with those units of temperature, right? I mean, I could have invented my own temperature scale, right? They're all arbitrary anyway. So, my 0 is a nice ball. What would that be? That would be like 78 degrees or something like that. Let's just see. Oh, like 82. So like the mean temperature actually in the summer is really hot here. So yeah, so 0 here is like 82. Why not? -2 is like 60 or something like that. I don't know. Seems like a good scale for temperature, right? As good as anything else. Okay, but ignoring that, now I actually am going to just exactly run the algorithm that I showed you before. So I'm going to repeatedly take my guess of theta. I'm going to start with theta being actually 0. And I'm going to just compute the error, compute the derivatives of that error with respect to my parameters, and just continually subtract off some small multiple. I think I actually don't say it, but by the way, for those that really want to know everything, and this will be all in the notes, but the number I'm using actually is that. Alpha, my step size is 0.001. Okay. Completely, dependent on, of course, the data and everything, so it doesn't actually matter here. I also am just summing up. I'm not like taking an average error per day. I'm just summing up all the days and taking that. So, if you divide by the number of days, then your alpha would be scaled similarly. But I'm just trying to give every bit of information about what I'm doing here. Okay, so here is how the algorithm looks. So here's the first iteration. So the first iteration, my thetas are actually just equal to 0 and 0. Right? So they're both equal to 0. So my slope and intercept are 0. And actually you can't see the line because the line is just down here. The line would essentially be just all zeros everywhere, right? It would have an intercept of 0, and it would have a slope of 0. In other words, it was just 0 predicts 0 everywhere. That's not a very good prediction, right? So to adjust the prediction, what we do is we can actually, this is kind of an optional one. We can just, while we're at it, form our error. That means that over all those days, the squared of all those differences between the prediction, which is always 0, and the actual one is this. Again, it doesn't really have any meaningful units, but that's a seemingly big number. And I can compute my two sets of partial derivatives there. So I can compute the derivative with respect to theta 1 and theta 2, just following exactly the formula that we had in the previous slide. Right? So after we do this, these are our gradients here. Sorry, our partial derivatives. I shouldn't say the word gradient yet. And now we're going to add a small multiple of these to this. Okay, particularly this small multiple here. Okay, so this is actually exactly, we're just going to basically multiply these, move these over the decimal places 3 plus over, and that's going to become our next guess of theta. All right. They're going to see actually why theta is actually exactly that thing, because we just multiplied those by 0.001 and subtracted them from theta, which results in theta being 0.15 and the intercept being 1.24. Okay, now with that, now you can see some of the line, right? Now the line's starting to creep up. So here's the line now to fit to this data. We do it again. We compute the error if you care. The error is lower now. That's a good thing. We're actually trying to make this error as low as we can. So it's a good thing that we're able to get it lower and lower with each step. We compute the partial derivatives again. Those are getting smaller too. That's another important thing. They're getting smaller because we're getting there's less sort of when we get to a solution, they're actually going to be 0, right? Because when we get to a solution here, this will come back again. But at this point here, the actual slope there is 0. And it tends to go down the closer you get. So here it's bigger than here, etc. So let's just keep going. Same thing. Compute the derivatives, add a multiple of them to that, and next line we get is this, and we're just going to keep doing this. So we have our theta, our error is now 64. That's looking better. Gradients are there, and just keep doing these updates. So here's the next one, iteration 5. I'm going to skip a few now, and here's iteration 10. Now at this point, our error is, over the course of everything, is just 7. Basically, if you take all the predictions minus the actual values, square it, add them all up over all the days, you get 7.09. And our gradients, though we could keep running to get them actually down to 0 here, we're sort of close enough and we can kind of stop right now. Now, importantly, if we do want to make predictions, not in our normalized temperature space. I mean, most people won't give forecasts in my normalized temperature scale. So if we want to go back to the real thing, we have to scale these things. And I think I actually didn't put what they are on the slide, but we have to scale them just by some fixed formula to get them back in our original coordinates. But this plot will just show what that looks like in the original coordinates, which is the same line, but just a version which has the high temperature. And all it really does is scale the slope by something and actually add something to the intercept to make sure that all the terms are accounted for. And again, the actual formula, if you want to know, will be in the notes, but it's hopefully not too hard to see that you could just do that. Okay. So now, the important thing about our model, in some sense, is it lets us make predictions. Right? So it's great that we sort of have a line that, given all the existing data, can kind of fit it. Seem like it can kind of fit it well. Right? And we'll actually see later on in this class or the next one that we can actually fit that exactly. We can actually come up with a closed form, just solution for what those two parameters are. But the more important thing than that, actually, the more important thing than just sort of finding a low, minimal cost set of parameters, is that this model lets us make predictions. So what we can now say is, if the high temperature tomorrow will be 72 degrees, which again, it actually will be tomorrow. I don't know if there's going to be air conditioning running yet, but there actually might be. It's in some places, which is pretty crazy. If we know there's going to be 72 degrees tomorrow, ignoring for a moment that that's also a prediction, let's just say that weather forecasts have a lot going for them. They're pretty good, so let's just trust that. All we do is we take our scaled version of our model, right? So this is now the scaled version that works in the original coordinates. We take our 72, we multiply it by our slope. That's in this figure. We add our intercept, and we get a prediction of 1.82 gigawatts. In other words, we take this figure here, we just trace to where 72 is, we look at where the line is, and we say we're going to predict that much. Now the important thing is that it could be off, right? Historically, there is certainly some error here. Sometimes we miss high, sometimes we miss low, but it's about as good as we can do, right? Because you can't we're talking about making single predictions here. If you can make a whole range of predictions, that's actually a very different setting. But if we're making a single prediction here, then you probably kind of want to predict in the middle of this, or the average value here, rather than trying to get this one exactly right here, because at least in the data we have, there's no way to differentiate this day and that day if all you can look at is their high temperature. So you kind of predict it's going to be kind of the average value here. That's the prediction we make when we get a new day. We're looking at a new day tomorrow. So this is really just equivalent to finding the point on the line. But again, this is sort of the crux of machine learning, is that we don't just get kind of predictions for the days that we already are building our model on. That's actually kind of boring because we already know what the answer is for all those days. What we actually get is we actually get a model, a sort of a new function, where we can feed in some new set of data to it and get out a prediction of what we expect the answer to be. And in fact, this is really kind of the crux in some ways of what machine learning really is. So let me ask one question now. I got this question before, but what do you expect would happen if you run gradient descent without first scaling those coordinates? So I told you it won't work. What do you think won't work about it? Say I run it with my same parameters I'm running at that one, alpha or whatever, or maybe I need a bigger or smaller alpha. What will happen if I try to run it without first scaling things? So let me open up the poll. Again, I meant this to be a multiple choice poll. Hang on a second. For those who have already voted, it's fine. Man, I always miss that option there. Okay, hang on. Okay, now if you reload, for those who haven't voted yet, if you've already voted, don't worry about it. If you haven't voted yet, more than one of this can happen. Actually, I guess the only one I guess actually these could both be true. That would be kind of odd, but more than one can happen. So you can check multiple choices. So let's see what people think. There's actually a lot of sort of middle of the road stuff, but I guess some of that was biased by the fact that a bunch of people answered it first without. Okay, boy, this is also indicative of lecture prep and a homework almost due. Okay, so who wants to argue for number 1? So 33% of people said the algorithm converges, it may converge to the incorrect solution. Who wants to say why that might happen? I know some people answered that, so. Anyone? So the idea is that it's easy to go to local optima here, okay? Does anyone want to say yes or no to that? Want to argue with the 60%, 2/3 that said no, it doesn't happen? Does anyone want to argue that? Yeah.
Well, I think the degree of the function is such that it probably doesn't have many local minimums.
Yeah. So unfortunately, I don't know if I don't think we have the language in this course to talk about this, but this function actually doesn't have any local minima. This is a function with a single global optima. And that comes from the fact that it's what's called a convex function. So it's always kind of curving upwards, and it never can kind of do things like this. So the function will not, this function, not general but true about machine learning, but this function will not have this kind of patterns like this. I maybe don't want to emphasize that because we don't really talk about the mechanics you need to prove that here. But it's actually a maybe 30-minute proof to get to that point. It's actually quite straightforward. So we just aren't going to cover it here. But it turns out that actually that would be a good guess about why that might happen. But it turns out there actually are no local, not many, but there are actually no local optima here. So this one actually will not happen. It can happen that you converge somewhere and you stop moving, but you you aren't in the right spot. How about number 2? Who wants to say why number 2, the algorithm might diverge? Basically, will not ever reach a point that stops moving. Someone argue why it won't diverge? Yeah. Mm-hmm. Yeah, that's actually exactly right. So the alpha, so the real tricky part here is actually the alpha. So what happens when you don't rescale things is that you might need a different size alpha. That's the next question. But if your alpha is, say, too big, what can happen here is that, say you're here, and you take a step past the optima that puts you over here, then you take this step that puts you over here, and this step puts you over here, and you just actually kind of start shooting back and forth, getting bigger and bigger each time. This is not a hypothetical thing. This happens all the time. So actually, if, and in fact, maybe evidenced by the thing, though, again, with the bias of only being able to select one answer, this is actually almost certainly going to happen if you don't rescale things, at least when you try things out at first. And even actually, if you do rescale it, if you just pick your alpha a little bit too big, this might happen to you as well. So you have to be a little careful with this one. And if you do that, what you'll see is you'll see your error function just kind of spiking and actually growing up exponentially, which is never a good thing. So yeah.
Why would you not be able to pick a smaller alpha function until it works with whatever scaling you have?
Yeah. So the question is, why can't you just pick a smaller alpha function? Okay. So this is actually the crux. Yeah. So this is the crux of the issue here about why. So okay. So we've said that I haven't scaled it, but why can't I just rescale it a little bit and pick a smaller alpha or a bigger alpha, whatever. I'll actually answer this last one. So actually, I mean, in this case where the units were much bigger at first, you will need a smaller step size to ensure convergence. If your original units are very small, and you actually inflate them, then you actually will need a bigger step size. So those are both actually possible, but in this case, you need a smaller step size. Okay, so why why do you have a hard time converging just by picking a smaller alpha? Yeah, so there's a. The question is, how do you decide the value of alpha? So again, this is the free parameter you have with gradient descent. There are all sorts of rules of what you should pick, or ways to pick it, but the reality is they're all rules of thumb. So it depends on the data. It depends on how you scale it. Now, with the scaling we've used, and actually also, you typically actually also want to normalize by the total number of days, so that you're talking about an average loss. There are certain rules of thumb about how you pick it, but the way you really pick it in practice for a fast one like this is you run it once and see if it blows up, and if it does, you increase it by like a factor of 10. If that works and it's still taking too long, you raise it a little bit and you do binary search until you find the one that works. Literally, a lot of actual production deep learning methods will run gradient descent. Oh, I shouldn't stand on that until the thing stops. The error stops decreasing, and then they'll just cut alpha by like a factor of 10, and then it'll decrease again, and that's actually how they work. So there are these rules of it, but they're really hacky. Now, for functions like this, there's actual also things you can do with line search. So you can actually also basically look at how your function changes with different size alphas, and then pick the kind of the biggest one that decreases the function by a certain amount. But that is actually not common in a lot of machine learning because it doesn't quite work with what we'll call stochastic gradient descent, which we'll define in a few lectures from now. So it's actually more common to just sort of pick something with a rule of thumb and decrease it if you haven't converged well, or increase it if you're going too slowly. The question, yeah?
What if we have multiple minimas in our function? How can we overcome that? Because if we have alpha too small, it will reach one of the minimas, and that might not be the actual global minima of the.
Yeah, so the question was, if you have multiple minima, how do you know alpha to pick? We're not going to really worry about that. Getting stuck in local minima was thought to be a really big problem for a long time. And it's people have kind of gotten off of that as a problem. People don't really worry about that much anymore. It turns out the landscape of a lot of optimization problems like this is such that you don't actually get stuck the way you think you might in local optima. Yeah. Yeah, so the question is, do we always deal with convex functions and not concave functions? Concave is the opposite, because concave is like this, just for people that don't know those terminologies. Yeah, so if you're dealing with a concave function, you're usually trying to maximize it. It doesn't really make sense to minimize. Usually, if you want to minimize a concave function, you can just go infinitely far away and you're done. If we're trying to maximize a function, we just think about minimizing the negative of that function. So we typically deal with minimizing it, but either way, it's fine. Maybe one more question, yeah.
Don't we need to also normalize the y?
That's a great question, actually. Don't we need to normalize the y values too? You can, but you actually don't have to as much for two reasons. So if they were really off, then yes, you'd have to. But the big thing here is that you just want to make sure that all the numbers are kind of in the rough, approximate same scale, and that they have sort of similar, at least in the case of x's, they have some negative and some positive values. In the case of the inputs, at least. The y's don't need to have the negative or positive values. That actually is taken care of by the intercept term to a bigger degree. And it doesn't really matter as much in this case, scaling the y's. It doesn't lead to a huge speed up because scaling the y's, well, actually, I don't want to get into too much the technical details here, but basically, in this case, it doesn't matter as much scaling the y's. You can kind of get away without doing that here because they're all already kind of in the same approximate scale. I mean, here, let me hide this. If you look at kind of our normalized setting, it goes from negative 4 to 2, and this goes from 1.5 to 3, so it's kind of a similar range, and it works well enough. If you have a huge range for y, you might want to, but really, actually, you can get away with just picking a different alpha in that case too, and so things kind of work out okay. If they're really biased by a high amount, then you need to actually deal with your intercept being a little different. But if they're as long as they're kind of scaled, and span a reasonable range, then things kind of work okay. all very kind of rules of thumb, and there's just things to try, and you certainly can normalize the y's if you want to. Okay, so now, in order to introduce kind of the general machine learning framework, I want to kind of ask a few broader questions now. So what if we wanted to add more features rather than just, temperature, like the day of the week, right? So people might use more power on the weekdays and the weekends, or at least, since they're in big office buildings, the consumption might somehow be different. What if we want to use a different loss function? Instead of squared error, what if we want to use absolute error or something like that? What if we wanted to predict, fit a nonlinear surface to that line, or to the actual data, not the line? If we don't want to fit a line, if we want to fit a nonlinear surface to it. Now it turns out that all these things are actually really easy to reason about if you just adopt a little bit more formal notation. And so actually what we're going to do with the rest of the lecture we have here is just kind of define the notation of machine learning and talk about kind of what the different aspects of machine learning algorithms are. Okay, so now we're going to talk about machine learning. We're going to kind of use this example to talk about machine learning notation in general. And this actually will be kind of the crux of, I keep using that word this time, I don't know why, but it will be kind of used throughout the entirety of our machine learning sections in this course. Okay, so what we've just seen is an example of a machine learning algorithm. In particular, it's been an example of what's called a supervised learning algorithm. Now, as I said, least squares predates machine learning, the term, by at least 200 years, probably more. But it's actually a great example of a machine learning algorithm in some way, a prototypical example in a lot of ways. And the basic idea of all machine learning, or at least, again, probably all supervised learning here I'm talking about, is that there's many domains where it can be really difficult to hand specify a prediction, or really a program that can make some prediction from data, right? So if my input data is the temperature, it's very hard to write a program by hand that can predict what the peak power is going to be. What's often, or in a more sort of contemporary machine learning example, if I'm given an image of a dog or a cat, it's very hard to write a program that just takes those pixels and determines is that a dog or a cat. But what's much easier to do is to collect a lot of data with the inputs and the correct answers. I mean, it's not trivial because you still have to get someone to tell you what the answers are. But in a lot of cases you can, at least relatively easily, collect a lot of data that tells you here's my input and here's what the output should be. So in the case of our example, the input was our temperature, maybe other things like the day of the week, and their output was the peak power, right? In the case of image classification, the input's it's a bunch of pixels, and the output is, is it a dog or not a dog, right? And so that's the idea of at least supervised machine learning. Now the process here is that we take this collection of input-output pairs. This is where we know we have the input and we know what the output should be, and we feed it into a machine learning algorithm. What this function produces is what's called a hypothesis function. It builds some function, which we're going to call h here, such that when we feed in our examples, our x's, into this function, it will produce something close to the outputs. That's what we had before, right? Our prediction here was that linear function of the input, and it tried to predict something that was close to what the actual output is, where we measured closeness by this loss function. And finally, the real sort of usefulness of this is when we have some new example we haven't seen before, we can feed that into the same hypothesis function and get a prediction out of what it thinks the output is. So the sort of catchphrase I like to use to describe machine learning is that in some ways it's kind of data-driven programming, right? We're building a program here, a hypothesis, but we're doing it in a way where we don't have to specify it manually. We're letting the data kind of tell us what that function actually is. And frankly, the massive availability of data has made these techniques kind of one of the only ways you could ever think about solving certain problems. There's just some things that are incredibly hard to program manually, but very easy to collect lots of data for. And these are things where machine learning has been incredibly successful. All right, so now I want to describe kind of get down to brass tacks and talk about the actual notation we're going to use really throughout this entire unit here. So I'm going to write it for this reason. Okay, So the notation we're going to use is the terms relevant to machine learning are first the notion of input, and sometimes we'll call them input features. And these are, we're going to denote x superscript I to denote the ith example. And each of these is a vector in Rn. So they have n dimensional input features. And here I goes from 1 to m. So very important here. And this is going to be sort of pretty consistent throughout the course. So remember these two letters. N here is the dimension of the input. Right? So in our case before, actually, it was just actually really one or maybe two-dimensional, depending on how you count it, whether you count the intercept term as being a feature or not. We actually will for the most part. I'll get to that in a second. And m is the number of samples, or examples, we'll call them. So remember those two terms. And we index with superscripts to index over the different samples, and subscripts will index into the entries in that vector. So we'll use things like x, I, j. That's equal to the ith example and coordinate j. Okay, for example, one input feature could be xi equals the high temperature for that day. A flag, like say a Boolean flag that says, is it a weekday or not? So that would be a flag that would be a number that would be 1 if it was a weekday and 0 otherwise. And then this is actually a little bit interesting here, but we're actually going to, in general, put in a constant term into our features. So rather than have a separate offset term, we're actually just going to build in the 1 into our feature. And the reason we do that is so that we can express our entire linear function, for example, as just a product of parameters and features. Right? So it'll cover, our hypothesis will cover both the slope and the intercept terms of our approximation function. Okay. And in general, this is always going to be the case that we have our inputs are always just going to be thought of as vectors in Rn. So there's real valued n-dimensional vectors. We'll talk a little bit later about how when we have things like discrete inputs, how do you actually input that into a machine learning algorithm? And it's not very hard, but we'll talk about that. Okay, so number 1 is these input features. Number 2 are the outputs. And this we're going to call yi, and they're in some class y. And actually, I'm leaving that kind of as a general class because there are two cases we're going to consider. One case is going to be the setting where y is real valued. So and this was the case we had here. It takes on a real number. This is actually called the regression setting, where y is real valued. But y can also be discrete valued. And in that case, the difference between the outputs being discrete or real does make some difference to the algorithms. And in particular, if y is discrete value, we call these classification tasks. So if it's discrete and binary, we call it a binary classification task. If it's discrete and multivariate, we call it a multi-class classification task. So again, here we had this example of yi, in our case, which is the peak demand. But if it's real, this means we're in a regression task. Okay, the next sort of component that we're going to think about are these notion of parameters of our model. So we already saw that, the parameters we had before, and we're going to use the same term theta to describe our model parameters. And for now, I am going to say that theta is also going to be a vector in Rn. So again, pay attention to these dimensions here. Rn, again, is the dimension of the input. And I'm, for now, defining my number of parameters to be the same as the size of my input. And we're going to do that especially because we're going to have this linear hypothesis function that I'll talk about in a second. But that's not a strict rule. That is a feature of these linear models we're going to consider for the next few lectures. Yeah?
For x times g,
Yeah.
so what is the range of g?
What is what?
The range of g.
J can go from 1 to n because x is n dimensional. So the question was, what is the range of j? J can be 1 to n because x is n dimensional. And so you can index it into the jth coordinate. And so there are only n coordinates of x. And I, of course, ranges from 1 to m because there are m examples in our data set. So, and also, when I write theta here, this means, the vector in Rn of all parameters. If I want to talk about a single value of theta, I would say theta j, right? That would be the jth element of theta. And finally, the final ingredient is our hypothesis. Well, not quite the final ingredient, but a final ingredient is our hypothesis function. This is a function that takes inputs and outputs outputs. So this is a function which we're going to call h subscript theta. I use this notation because I want to emphasize the fact that it depends on theta, but I don't want to really define it as a function that takes as theta as an input, right? It is parameterized by theta, is one way we call it, but it's really fundamentally a function that maps inputs to outputs. So this is a function that maps inputs, in other words, things on our input, to our output space. Now actually, this is a little bit, we're going to change this up a little bit when we talk about classification, but this is the most obvious way of thinking about it right now, so let's just think about it like this for now. For example, a linear hypothesis could be h theta of x. I'll even say xi, just to sort of note that this could be an ith example on some data set. Would just be equal to the sum overall j from 1 to n of theta j and xi j, which, by the way, also is just equal to the inner product of theta and xi. I'm going to try to avoid too much vector notation, at least at the beginning. We're going to get to that later, next lecture. But this is sort of the basic notation here. I'm going to try to stick with this one for now, even though these are, of course, equivalent. There. Okay, any questions on this? Yeah. Yeah, so the reason why I have a bias there, the question is why is there a 1 there? So in general, at least initially, I'm going to put my intercept term as a feature so that I can write my model with an intercept term while writing it as kind of a pure linear function of the input. This is sort of for convenience. You certainly can have the intercept term be separate, but it's a little bit more convenient typically to have it be to actually have it be a feature. And then the math works out a little simpler. Right, so basically, in the case of the high temperature, if you only had one feature, right, that's basically the high temperature and then the 1. Theta 1 multiplies high temperature, and theta 2 multiplies the constant term, i.e. it's just the intercept. Yeah, the question is that 1 is included in n, so yes, in our case, the 1, so that would be a vector in R3, so the 1 would count towards the number of the dimension of the input. All right, so a couple more ingredients here. I'm not going to quite get it all on one slide, unfortunately, or I probably should have written this a little smaller, but let's see how much I can kind of I'll write one more thing here, and then I'll write the next thing on the next to the paper. All right. The next ingredient that we sort of care about. As a question? So this is remember, this is our inner product notation. So when they are both vectors, this is just equal to that. Those two are just equal. This is an inner product, thought of as column vectors. So if that sort of doesn't, if you don't remember that, I'd go back and look at the linear algebra lecture where we covered that. Okay, so the last element that I'll mention here is the notion of a loss function. So remember, what we wanted in our machine learning model is for the hypothesis to approximately give us the output when we feed it when we feed in our examples, right? So we want yi to be approximately equal to h theta of xi for all I. Right? That's what we like to have. So the question is, how do we measure kind of approximately equal? We probably don't want to force it to be exactly equal, right? That seems very strict. We actually know we couldn't, for example, fit a line that was went exactly through all those points because some of them weren't on a line. But we want it to be approximately equal. Now, the way we're going to formalize this notion of approximately equal here is through a loss function. In particular, a loss function is going to be a function L, which takes outputs. This first one is going to be the prediction. The next one's going to be the true label, though they can be swapped sometimes. And it's going to output a positive real number. So we assume losses are always positive. There's some measure of how good or bad our predictions are. And so if our loss is 0, we actually say that we're exactly predicting our output. This is equal. When these two things are equal, the loss is always 0. If the loss is big, in some sense, those two are far apart. So while there's a lot of choices we can make for loss functions, the squared loss seems to hit all those criteria, right? So I'm calling y hat here our prediction. So we have our prediction, our actual output. And one possibility for the loss function would just be to take the prediction minus the actual and square it, right? So if those are the same, obviously that's equal to 0. If those are different and very far apart, if they're different, it'll be non-zero. And if they're very different, it'll get bigger and bigger. So it captures some notion of, how well are we predicting this if we can get a low loss, which is exactly what we did before, right? We just minimized our loss function of our predictions. Okay, and now you know enough for me to write down every single machine learning problem that there is, which is just that problem there. So every single machine learning algorithm that exists is every supervised algorithm, though actually, to be honest, you could even frame unsupervised methods in this same framework, which we will do later. But this leads us to the canonical machine learning problem. And I do think it's important that when you see different algorithms in machine learning, you bring it back to this canonical problem here. Because they all are of this form, despite the fact that people justify them in completely different ways and describe them very differently. They're all just of this form. We want to minimize over theta. So this means, this notation just means that we're going to pick the theta that tries to minimize some objective, it's called. The sum from I equals 1 to m, that is over our whole data set. So sum over all the examples of the loss between our prediction, which is our hypothesis applied to that example, and the actual label of that example. And with a few minor additions to this, this is actually every machine learning algorithm. So everything will fit into this framework. I'll talk about a few in the next slide, but if we have time. But importantly, what this actually means in practice is the following. It means what actually constitutes a machine learning algorithm is just 3 different ingredients. So to specify a machine learning algorithm completely, you first need to specify your hypothesis function. I need to say what is the function I'm going to use here. And this is actually one of the biggest differences, of course, between different algorithms, right? Deep learning and neural networks are different from least squares, primarily because they have a different hypothesis function. Everything else is actually pretty similar. 2, so that's this part here. 2, I need to specify my loss function. I need to specify how it is I'm going to measure being approximately equal on my data set. And 3, I need to specify an optimization procedure. I need to say, how am I going to find parameters? Those are the things that specify what my hypothesis function is. How am I going to find parameters that minimize this sum of loss functions here? And just to give a quick preview, as I like to say, we in machine learning are very good at coming up with clever sounding names. And so you will hear all sorts of names for machine learning algorithms, things like least squares, linear regression, support vector machines, neural networks, decision trees, naive Bayes. They're all things that are used and sound completely different. People talk about them in very different ways. But they are all just instantiations of those 3 things. Right? So least squares is linear hypothesis class, squared loss, and actually usually least squares refers to an analytical solution, which we'll cover next time. Linear regression refers to a linear hypothesis, and actually that's all it does. It could refer to squared loss, but it could also mean like an absolute loss. It could mean anything there. And there are actually different ways of solving it too. So one thing we are not very good at in machine learning is being specific about what we mean when we say algorithm. So we will frequently define an algorithm and say only one of the things. For example, a support vector machine usually uses a linear or a kernel hypothesis class and uses hinge loss usually. But actually, you can use whatever optimizer you want and still be a support vector machine, despite the fact that they're different algorithms then. And similarly, a neural network is primarily a certain class of hypothesis functions, but people almost always, and actually they can use kind of whatever loss you want, but they're almost always optimized by gradient descent. So really what it is there's this sort of big collection of algorithms that specify some subset of these, and people all refer to them kind of equivalently. So this is what actually makes machine learning confusing in a lot of ways. And libraries use this all inconsistently. So some libraries will call, they have to have all of these things actually run, so they have to say, pick something for some of them. And that makes it quite confusing in a lot of ways. But what we'll see, and hopefully what you can kind of start to appreciate as you go through it yourself, is just how every algorithm you will ever encounter is just instantiating those 3 elements. So we'll talk about that more next time.